If you remember last time, we had a look at simple harmonic motion, and a not uncommon exam question is to say, can you define what's meant by simple harmonic motion? All right, so you've got this already, but let's just go through it. Imagine this was an exam question. It would normally be a couple of marks maybe. It's quite a complicated thing, okay? As I said last time, build it up in stages, all right? First of all, what does a harmonic motion mean? It's just another word really for an oscillation. All right, what do you need for an oscillation? You need two things. Number one, you need an equilibrium position. You need somewhere in the system where it can just settle down and stop. All right. Secondly, you need a restoring force. Okay. So how do you get an oscillation? You have an equilibrium and you have a restoring force. And a good way to think about this, as always, think about a pendulum. The equilibrium position is there. If you let the thing swing for long enough, it will settle down, and the tension in the string pulling upwards and the weight of gravity pulling downwards, those two forces will be the same size, okay? And the thing will settle down there. Importantly, if you displace, we don't use the word distance in SHM because it's critical that we understand whether it's plus or minus which side of equilibrium. So you can either have an x displacement that way, which is plus, or you can have x being displaced that way, which is minus, okay? If you displace it this way, then the force will act that way. We saw that last time. Remember, we took the weight and we took the tension, and we resolved them, and we found there was a component, the horizontal part of the tension pulls the thing back towards the equilibrium. If you displace the pendulum to that side, which is a positive displacement, you get a naught force which is negative that way. All right. So in this little system I've defined, we've got plus that way and we've got minus that way. All right. So plus and minus is very important. That's why we use displacement, which is a vector, rather than just distance, which is a scalar. And very importantly, we can see this is a restoring force because whichever way you displace it, you'll get a force in the opposite direction, basically back towards the equilibrium. Okay. If you do those things, if you have an equilibrium position and a restoring force, then you'll get this. You'll get an oscillation. You'll get harmonic motion. All right. Can anybody remind me what's the extra bit we need to get simple harmonic motion?
Force is proportional to the displacement.
That's it. We need this restoring force to be. We need an extra bit added on. This needs to be proportional to the displacement. Okay. And I really ought to put in there a minus sign because opposite directions, aren't they? All right. Remember here we're talking about vectors. I don't know how you do this in maths these days. I put little lines under things to show they're vectors. All right. This thing here isn't just F, 6 newtons. It's a vector. So 6 newtons means that, and minus 6 newtons means that. All right. If that's the case, then when the displacement is plus, you want the force to be negative. When the displacement is negative, you want the force to be plus. And the only way you can do that is to put in a minus sign. That's why the equation for SHM is often written like that. Okay? Displacement is equal to a constant like 10 or 93 million or something like that. If you times displacement by a constant number, you get the force in the opposite direction. Okay? It doesn't look much, that equation. It's kind of got all of this built in. Okay? So an equilibrium and a restoring force will get you harmonic motion, but if the restoring force is proportional to the displacement, if I pull my pendulum twice as far away, I get twice the restoring force. If I put it 3 times as far away, I get 3 times the restoring force. If that's true, then I get the special kind of harmonic motion called simple harmonic motion. Does that make sense? All right. That bit on the board, we did all that last time, but it's worth having that in your mind because it's not uncommon. They say to you, what is meant by simple harmonic motion? Define what's meant by simple harmonic motion, etc., etc. Okay. One thing we didn't do last time, it's worth just tying up, is you might think to yourself, well, why? What's so special about simple harmonic motion? Why are we bothered if the displacement and the force are proportional to each other? Well, it turns out, if this is the case, if you've shown that force is proportional to displacement and you've got simple harmonic motion, then you get basically this bonus property, all right, which turns out to be incredibly useful. What it means is that the time period is time period is independent of amplitude. Remember amplitude? Yeah, the distance the side you pull it. So if you get your pendulum swinging like that with a small amplitude, here it is swinging with a big amplitude. Yeah. It turns out that doesn't affect the time period. Okay? So why would you go to the bother of checking that the restoring force is proportional to displacement? It's because it brings you this property. We won't go into the advanced maths of it, but if the restoring force is proportional to the displacement, then you get this. You get the time period being independent of amplitude. Now that is tremendously useful, and from the earliest times has been used for measuring time. Think about it. You've seen clocks that work by pendulums? Yeah, in fact the earliest clocks, that all they worked by, wasn't it? Yeah. So you get your pendulum swinging, and you get it swinging, and you have a gubbins at the top of the pendulum, so as the pendulum moves, it makes the clock hands go round. That's how clocks work, all right? But you might say, well, this is never going to be a very good idea because it's swinging away quite happily, but when I come back in half an hour's time, you with me? It's only doing that, yeah? Surely it's going slower. Well, it's travelling slower, isn't it? Yeah? There it was travelling quickly. You let it slow down. We need to sharpen some of these words up in a minute. But if you take your pendulum moving quickly like this, and you say half an hour later it's moving much more slowly, but I point out to you its journey is much shorter. Are you with me? Here it's doing a big journey quickly, and here it's doing a small journey slowly. All right? If we're very lucky, those two things will balance out, and it will take exactly the same amount of time. And that's what simple harmonic motion is all about. All right? Simple harmonic motion is the motion where time period is independent of amplitude. A pendulum swinging quickly like this on a big journey, and a pendulum swinging slowly like this on a small journey, they take the same amount of time. All right? Make quite a good argument. So if you can imagine a pendulum doing that, and the same pendulum, very important, that isn't the same pendulum, is it? The same pendulum doing that, they will have the same time period. Okay? Not all systems are like that. Are you with me? Some things oscillate, some things do harmonic motion, and that isn't the case. Okay? So why in physics do we get so excited about simple harmonic motion? Why do we check out that the force, the restoring force, is proportional to displacement? It's because it will give you that property. All right, we'll look at it in a bit more detail later on, but basically that's fundamental to using oscillations to measure time. All right, and if you think about a pendulum clock or something, some of them run for days, don't you? Get clocks that run for like 7 days or something like that. Yeah, and obviously when you start them off, they're swinging like that. And when they're nearly run down, they're swinging like that. But because they're doing simple harmonic motion, it doesn't matter. Yeah, that's the reason that pendulums and things are used. And springs, talked about springs doing SHM. Watches, old-fashioned watches with it's not a boingy spring like you use in experiments, is it? It's a round spring, yeah, but it's the same thing. You wind it up and it unwinds. Springs do simple harmonic motion, of course, that's why it's used in clocks. Okay, we need to have a look at some examples. Good news here, if you're thinking simple harmonic motion, possibly one of the worst bits of A-level physics, they kept it right to the end to just be horrible. You're kind of right. The good news is, though, there aren't that many things that do simple harmonic motion which they can really ask you about at A-level, all right? So we all know the bit of physics we don't like, which is the fact that you turn up to the exam and they give you a situation you've never seen before. You with me? Anything? Never seen this before, got to work out. Some good news here. How many things can they sensibly be asking you about? Well, we did the pendulum. Look at the pendulum. And we had an equilibrium. Yeah, down the middle. We showed that there was a restoring force, like we did just now. Okay, and we showed that restoring force is proportional, sort of. Yeah, do you remember we had to cheat a bit, didn't we, with the pendulum? If you analyse the forces and work out the horizontal component of the tension that's going that way, which is the restoring force, is it directly proportional to the distance you pulled it to the side? Not really. We get sines and cosines and stuff involved, don't we? So we had to cheat a lot and basically say for small angles. Okay, less than about 10 degrees, yeah, it is, sort of. If you take a pendulum at that much to the side and you pull it twice as far, you will get twice the displacement. You will get twice the restoring force. Okay? If you do that and then do that, you won't, all right? If your angle is like 45 degrees, that's not the case, all right? So for small angles, the pendulum works. Okay. The one we did first last time, which is actually much easier, is the spring. Okay. You can buoy your spring vertically if you want to. It works the same. Okay. And for that one, there is obviously an equilibrium. There's a restoring force, because if you pull the spring that way, the force wants to pull you that way. If you push the spring this way, the force wants to send you that way. Okay. And restoring force proportional to minus displacement worked very well because of a piece of physics to do with springs called Hooke's law, which says almost exactly that. All right, springs are defined to have that property unless you go bonkers with them, where the amount of displacement and the amount of force are proportional. Okay, so that worked well. Okay. Now, to be honest, if you look at A-level papers, most exam questions are these two. Yeah. Sometimes they say, here's a spring in a car suspension. You go, steady. But you can see really easily it's a spring. Are you with me? So this is not a nice area of physics. It looks very, very complicated. It's easy for it to get very mathematical. The good news is there aren't that many examples of things. All right? Newton's laws of motion, nice and easy, F equals ma. But you open your paper and it's a spacecraft going to Mars. And you think, what? Where's that come from? Because they can apply it to a whole range of things. All right? So the Achilles heel of this section, if you're taking the exam paper rather than setting it, the Achilles heel of this paper, this part of the paper, is they don't have too many questions on it because it's horrible, and it's going to be pendulums or springs. Yeah? And I don't quite know why, because there's a lovely example of simple harmonic motion. An example of simple harmonic motion is a floating object. Get a block of wood, put it in some water, yeah, push it down. Does that, doesn't it? Yeah? So let's see how it works. Have we got an equilibrium position? Yes, we have. You with me? There's the point where it would float naturally. All right, it'll naturally settle down there where the upthrust force, do you remember Archimedes' principle? If you push water out of the way, that weight of water pushes you back. So that's the upthrust force. And the force of gravity, weight. When those two are equal, yeah, it just floats. That's the equilibrium position. If I push the block down, so let's try and draw it a bit better actually. That's very clear, is it? So you've got, for a floating object, you've got an upthrust force because of the weight of the liquid displaced. You've got the weight pulling down, okay? Let's suppose I took my object that sat there happily in equilibrium. Let's suppose I pushed it under the water a bit. I forced it to be a bit further under the water. Which of these two forces would change? Yeah, the upthrust would get bigger, wouldn't it? So if I push that under the water, I'm going to displace, that's the word we use, isn't it? When you push something under the water, you displace more liquid. Why is the displacement of liquid important? Because it's the weight of that liquid that pushes back and creates the upthrust. So if you get something that's floating and you force it further under, yeah, then you're going to increase the upthrust. What's going to happen to the weight? What's going to happen to the weight in that situation, the weight of the wood? Stay the same. So look at those two forces. I've increased the upthrust and kept the weight the same. What's going to happen? There'll be a resultant force upwards. So if I push something down, if I displace it that way, I'm going to generate a force that way. Let's suppose I take a floating object and I pull it up slightly, so it's sitting higher in the water than it really ought to. What's happened to the amount of water it's displacing? It's less. So what's happening to these forces? Which one gets bigger, which one stays the same?
Weight stays the same, upthrust gets smaller.
That's it, the weight stays the same, doesn't it? But the upthrust now is smaller. If you pick the object up slightly, it's not displacing as much liquid, there won't be as much upthrust, and the resultant force will be down. If the upthrust gets smaller and the weight stays the same, so if I displace it this way, I'm going to have a resultant force that way, all right? So here's a good example. We've got an equilibrium position. We've definitely got a restoring force, yeah? Because whichever way you displace it, yeah, you get a force in the opposite direction. So that's going to give us an oscillation. Why is it simple harmonic motion? Well, kind of obviously, really. If you push it 1 centimetre under, and then you push it 2 centimetres under, how much more water have you displaced? Twice as much, yeah? So it's kind of, unless the object's a funny shape, imagine if it's like a rubber duck shape. You with me? You push it 1 centimetre under and then you get to its neck. Do you follow? Then you wouldn't, would you? But imagine it's just like a cylinder, like a tube. If you push that under 1 centimetre, then you push under 2 more centimetres. You with me? You've doubled the upthrust, haven't you? All right. So this is clearly another example of SHM. All right. But the good news is, because this isn't a nice section, the good news is in the exam papers you're going to find lots of questions about pendulums. You're going to find lots of questions about springs or floating objects. I always think is a good one. Some good physics there. You with me? Up thrust in your syllabus. There's some good physics to think through there. Okay. Other ones I would think of is teacups. You can try this at home. Get a marble in a teacup. Yeah, there's a lot of friction, so it slows down quite quickly. Again, I'm not sure that's quite simple harmonic motion. It depends on the exact shape of the teacup. If you can look at an SHM system, identify the equilibrium, identify the restoring force, and show the restoring force is proportional to displacement, then you have SHM.